Okay, then we shall begin. This is your practice final, and it started off with all of these things here. So where is, let's try some of these here. Okay. All right, so we're going to see if any conditions have been violated. All right, and so the conditions as listed are independent and randomization, big population, large sample. So those are the three conditions. So is the independent and random condition met in this scenario? It says a study is performed to understand the relationship between bright lights and headaches. 80 randomly selected subjects are exposed to bright lights, and 20 of them complain they experience headaches. 90 subjects are exposed to less bright lights, and 12 of them complain about headaches. Are any conditions violated? Okay, so in the problem it says 80 are randomly selected and 90 are randomly selected. So this condition has been met. Okay. The next condition we want to check is big population. So what are the respective populations here? The respective population is anyone who may be exposed to lights and might experience a headache. Okay, so that's pretty much everybody, right? Everybody, unless, maybe a few isolated populations who are not exposed to technology or something like that, right? So this is pretty much everyone in the world. Okay, so did we sample more than 10% of our population? No. Okay, so this condition has been met, right? Because the big population, you don't want to sample more than 10% of the population, okay? Or, in other words, the population is much bigger than 10 times our samples. Okay, and lastly, we have the large sample condition. So in this case, we need at least 10 successes and 10 failures. Okay, and so what do we see? For bright lights, our success, again, these are arbitrary labels. Our success would be people who experienced headaches, right? So we have 20 who experienced headaches, so that's 20 quote-unquote success, which means how many failures do we have if 80 people were sampled total? 60, right? 60 quote-unquote failure. Again, arbitrary labels, not necessarily good nor bad, just 20 people experienced one thing, and that means 60 people did not. Okay, and then for the less bright lights, or the dimmer lights, how many successes do we have? 12, right? Okay, and so how many failures does that leave us? If we have a total of 90. So 90 minus 12 is 78. So we have 78 quote-unquote failures. So far so good with everybody? Okay. All of these numbers are bigger than 10, right? Okay. So large sample condition has been met. save this. Okay, so in this case our answer choice is D, all conditions met. We good? Okay, so I'm gonna keep moving on. All right, over here it says, researcher wants to make a confidence interval for how common a certain disease is. He finds 300 randomly selected subjects. Okay, so independent random has been met. Finds 2% of them have the disease. Okay, so big population. Okay, what is our respective population? This is everyone, right? Because we want to know how common a disease is. So it's just, this would be everyone global. Okay, so our population is much more than 10 times our sample. Let's check our large sample condition. Okay, so how many successes do we have? It's not listed, so our success would be n times p, and our failures would be n times 1 minus p. So in this case, I have a sample size of 300, and my p is 2%. So I have 300 times 0.02. I have 6 successes. My failures will be 300 times 1 minus 0.02. So that gives me 294 failures, okay? 6 is less than 10. Okay, so the large sample condition is not met. So our answer for number 2 is condition C is violated. Yes?
Question. How do you do the big population again?
So we just have to ask who is the respective population here, right? So all it says, we just want to know how common a certain disease is. So that pretty much means how many people in the world are there, how many people have the disease. So our population would be how many in the world. Okay, so a sample of 300 people is not more than 10% of the world population. Okay, it might be different if it said how common a certain disease is in the city of whatever, okay, then your population is much smaller. Okay, but it just says how common a certain disease is, period. It probably just means kind of on a global scale or national scale. Okay, questions? All right, I'm just gonna keep chugging along, all right? So if anything, you got questions about something, raise your hand, okay? Student has to conduct a survey for a school project. He goes around the school campus and interviews people he meets, finds data from 100 people and finds that 45 of them answered yes. Okay, so is this random? No. Okay, not a random sample. Okay, because he goes around the school campus and interviews. Okay, so this is violated. Okay, we can ask about big population. Okay, so our sample is 100 people. The population would be everyone at the school, right? Okay, and this is not specified in the problem, okay? So this would be violated if the school has less than 1,000 people. Because our population needs to be at least 10 times our sample. Okay. However, just the fact that we didn't get a random sample basically means this one doesn't even matter. Okay. The reason why we worry about big population is because if this condition is violated, it means we don't really have a random sample. But we don't have a random sample to begin with, so this doesn't even matter. Okay. And so pretty much, you know, if A is violated, B and C don't really matter, but we can check, okay? Let's do large sample. Technically this is met because we have 45 success and 55 failures, which mean and both are bigger than 10. Okay, yeah, Susanna.
But on the final, it could be more than one.
Yeah, you know, I've written my question so that only if there is a violation, it will be only one. Okay, I'm trying to make everything as unambiguous as possible. But yeah, you know, in real life, you're right. More than one condition could be violated. Okay, and then that really means you can't trust whatever conclusions they're trying to say. Okay. And so just be mindful of that, you know. A lot of times on the news they'll publish results of surveys, or they'll do a quick poll online or something about some topic, you know, how do you feel about this person doing this thing out over here? And if it's an online survey, pretty much those results are not useful for anything, okay? If they got their opinion by surveying people on the internet, it's not going to be not valid. Okay, so you know, American Idol and whatever other those voting shows, Dancing with the Stars and stuff. You know, they have online voting and voting via phone, and you can call up to this many times. These are not representative samples of the United States, okay? And probably not even representative of people who view the show, okay? Because if somehow we were able to track down everybody who views the show and we ask them, did you actually vote and how often do you vote? Not everyone's gonna say the same thing, and so you know, I think certain studies have shown that certain demographics and certain regions of the country are more likely to vote than other areas, and so sometimes, you know, sometimes the winners of the shows end up well, anyway, this doesn't even matter. Okay, so anyway, online surveys not useful. I'll just say. Okay. Lastly, number 4, a company wants to survey its employees that has 800 employees. It decides to select 100 of the employees randomly and interviews each of them. It doesn't even talk about successes and failures, but the point is here is our population has 800, and even if it selects them randomly, okay, so random selection, that's fine. So so this is met, big population is violated, right? Because the population is everyone at the company, which is 800 people, and our sample is 100 employees. So our population is not over 10 times our sample. So this one's violated. Okay. As far as large sample, this we have no idea, because it doesn't list the number of successes or failures or proportion. Okay, so there's no information specified here. Sounds good? All right, that's what I like to hear. All right, so let's take a look at this next thing. Okay, it says a farm wants to test 2 diets for their cows to see which diet causes more weight gain. They randomly select 10 cows to give diet 1, and they select 12 cows for diet 2. After 2 weeks on diet 1, the cows gained this much weight, and after 2 weeks on diet 2, the other cows gained this much weight, etc., etc., etc. Okay. And so in all of these questions, the most important thing is, do we have means or proportions, and do we have 1 sample or 2 samples? So what do we have? Means or proportions? Means, right? Because we see words like average, and we also see standard deviation. So these only appear when we have means. Okay? How many samples do we have? 2, right? We've got 10 cows for diet 1, 12 cows for diet 2. So we have means, 2 samples, and as we look at the questions, it says confidence interval, so we're dealing with a confidence interval. Is that okay? All right, so we can look at our study guide and whatnot, and it says for a 95% confidence interval, what will be the center of the interval? Okay? So this is going to be x bar 1 minus x bar 2. If you're not convinced, let me see. Why? Okay, let's get this here. Oh, I don't know where I put the study guide. So the study guide says for the center, when you're dealing with 2 samples, it's going to be x bar 1 minus x bar 2. So let's go through and list off our data here. Okay, so the data from the problem. So we have sample 1 and we have sample 2. And so we have x bar 1, S1, and N1. X bar 2, S2, and N2. And this will make all of our work easier if we just take a moment here to identify all of these numbers. Okay? So it says we select 10 cows for diet 1. So what's that? That's going to be N1. 12 cows for diet 2. That's N2. After 2 weeks on diet 1, the 10 cows gained an average of 15.2 pounds. So that's x bar 1. with a standard deviation of 4.1, so that's S1. After 2 weeks on diet 2, the 12 cows gained an average of 12.6 pounds, so that's X bar 2, with a standard deviation of 3.4. Is this okay? The labeling of all of these numbers. Okay, and again, as you guys take the final exam next week, I strongly encourage you to just take a moment to label the numbers that you encounter in the problem. It will just help. All right, so for number 5, we see our answer by checking our study guide is going to be X bar 1 minus X bar 2. So that is going to be 15.2 minus 12.6. My answer for number 5 is 2.6. Okay, what will we use for T star? Okay, so T star, it says 95% confidence. And how many degrees of freedom do I have? I'm going to do n minus 1, and I'm going to use the smaller n. So I'm going to have 10 minus 1, 9 degrees of freedom. Okay, so I go to my table and I look up 9 degrees of freedom, 95% confidence, 2.262. Okay, the standard error for number 7. Standard error, again, you can check the study guide here. Let me go ahead. I don't have, let me see if I could pull this up here. Here we go. Okay, so if you look at the study guide, it says what's the standard error for 2 sample means S1 squared over N1 plus S2 squared over N2. So it's going to be the square root of 4.1 squared over 10 plus 3.4 squared over 12. You punch this into your calculator and you get 1.626. Alright, so number 8 has us put all of this together. 2.6 plus or minus 2.262 times 1.626. And on the low end I get negative 1.078, and on the high end I get 6.278. Are we okay so far? Do we need any of this detailed out? Yes?
Did we find did you do the TS for this?
There's no TS because here we're doing confidence interval. Okay? TS, test statistic, only appears for hypothesis tests. Okay? So, yeah, so again, at the beginning, say, you know, I'm doing means, I'm doing 1 sample or 2 samples, and then say I'm doing confidence intervals or hypothesis tests. So there's no
TS for confidence intervals.
No TS for confidence intervals. Okay? Okay, so based on our 95% confidence interval, do you conclude that there is a difference in the average weight gain? So what do we look at? It goes from negative 1 point something to 6 point something. What do we say? Our answer is no. Okay? We do not have evidence of a difference in weight gain. Why is that? In weight gain between diets. And the reason is because 0 is a plausible value within our confidence interval. Okay? If our confidence interval is entirely positive or entirely negative, then we do have evidence of a difference. But in this case, 0 is a plausible value, so it's very possible that the difference between diet 1 and diet 2 is 0. Okay? 0 is within the interval. Okay? Are there questions on this? This is an important question, okay? You're going to see stuff like this. Yes?
So when zero is within the interval?
You do not have evidence of difference, okay? So if 0 is in the interval, that means no evidence of a difference. If 0 is outside of the interval, you do have evidence of a difference.
How do you find the 0?
So you look at your low number and you look at your high number. So my low number is negative, my high number is positive. Okay? So that means it crosses 0, right? Okay, because 0 is the divider between the negatives and the positives. Okay, and number 10, if we made a 90% confidence interval instead of a 95% confidence interval, what would happen in terms of our interval? Would it get bigger, smaller, wider, or more narrow? 90%, we lower the confidence. So a 90% confidence interval will be more narrow than the 95% confidence interval. Satisfied with that? Questions, issues? Yes?
So on the previous one, number 9, if 0 is outside,
If 0 is outside of the interval, you do have evidence that there's a difference. Okay? Okay, I'm going to go on. Okay, let's look at 11 through 16. Okay, so we're going to the very exciting ruler and yardstick factory. A machine is suspected to be defective. The yardsticks are supposed to be 3 feet long, and we're measuring a sample of 40 yardsticks and find that the average length is 3.02 feet. Standard deviation is 0.03. Is this evidence that the machine is producing yardsticks that are too long? That's what we want to know. Okay, well, are we dealing with means or proportions? Okay, so what are we looking at? We're looking at the length, okay? And we see words like average length, and we also see standard deviation, okay? If the standard deviation is given to you in the problem, it's a very strong indicator that you're dealing with means, okay? So we have means, okay? And do we have one sample or two samples? One sample, right? One sample of 40 yardsticks. Okay? And as we look at these questions down here, it talks about hypotheses. So we're dealing with a hypothesis test. Okay? Again, it's very important that we identify what type of test we're doing or what kind of situation we're in, as that will guide how we will do the rest of our problem. Okay? So let's take a moment and go through the data that is listed in our problem. Okay? So it says the yardsticks are supposed to be 3 feet long. What is 3? 3 is the mu 0, right? 3 is mu 0, what our null hypothesis states, yes. So our mu, okay? The random sample of 40 is n, so n is equal to 40. The average length, 3.02, that's x bar, right? And the standard deviation, S, is 0.03. Okay. Number 11 says, is this a one-sided or two-sided test? When we read the problem, it asks, is this evidence that the machine is making yardsticks too long? Okay? So that gives us a one-sided test. Yes?
What's the difference between a one-sided test and a two-sided?
So a two-sided test would have non-directional words like, is this evidence that the machine is producing yardsticks different from 3 feet? Or that is not 3 feet, or something like that. Or one-sided is if it's indicating, you know, are they too long? Are they too short? That's gonna affect things, okay? So for number 12, the hypotheses, okay, when we have means one sample and it's a hypothesis test, it's going to be mu is equal to some number. And that some number is 3. The sticks are supposed to be exactly 3 feet long. The alternative hypothesis looks exactly like the null hypothesis, except the equal sign is replaced with something else. And so what are we going to use here?
Greater sign?
Yeah, greater than, okay? Because we want to know, are they too long? So we're going to have mu is greater than 3. It's number 12. Okay, and so for number 13, now we're going to calculate our test statistic, okay? Our test statistic for means one sample hypothesis test is going to be x bar minus mu 0 over the standard error. My standard error is s over the square root of n, so I have 0.03 divided by the square root of 40. Okay, so I think that's something like 0.0047434. So my test statistic is going to be 3.02 minus 3. The number that shows up in my null hypothesis is 3, divided by the standard error of 0.0047434. And this gives me a number like 4.2. Okay, that's with some rounding. Okay, so that's number 13. Number 13 is 4.2, and we want to find number 14 is find the p-value. Okay, so when we're going to look up this number 4.2 in our table, and how many degrees of freedom do I have? I would have n minus 1. I would have 39 degrees of freedom, right? I go to my table, and I'm looking for 39 degrees of freedom, and I don't see it, okay? So we always round down. And we use 30 degrees of freedom. I know 39 is much closer to 40 than it is to 30, but we're going to use 30 degrees of freedom. And I'm looking for the number 4.2. And what do I see? I see 4.2 is larger than the biggest number in that row. Okay, so 4.2 falls on this side of the column. Okay, so, yes?
Why is it always rounding down if it's so close to 40? Is that just the way the laws are?
Yeah, that's the rules. It's kind of like if you're gonna throw a party and you have enough food for 39 people, should you invite 30 people or 40 people? To be safe, you're supposed to only invite 30 people, right? Okay, or maybe not food. Food is a little flexible, but if you have chairs, right?
It's just like a step of possible.
Yeah, it's kind of you gotta go down. Okay. Yes.
So you're looking the number up in the T table. You do your degrees of freedom, and then you're actually looking for the number that we got.
Yeah. So we're looking. Yes. So we do 30 degrees of freedom, and we're looking for 4.2. We don't see 4.2, but if we had to kind of place it, right? It doesn't go in between any of the other columns. If we were to kind of put these in order, 4.2 is bigger than this last number of 3.385, right? Okay, so we go to our column heading, and so 4.2 is bigger than the last column number, then that means our tail area is what? Bigger or smaller than 0.001? Smaller, okay? So again, don't get confused. The test statistics get bigger as we go this way, but the tail area gets smaller as we get further away from 0. Yes?
Do we have to subtract one from anything?
You don't have to subtract 1 from anything, okay? You don't have to worry about that, okay? So we see 4.2 is bigger than, I think 3.384 was the number in that table. Yeah, or 3.385. So that means, so our tail is less than 0.001, okay? Because it's a one-sided test, I don't have to do any doubling. My tail is my p-value, okay? So my p-value is less than 0.001. Okay, so our p-value,
And that's just enough of an answer?
and that's enough of an answer, okay? When you use a table, you're not going to get precise answers, okay, when you use a table like this. If you had a calculator or a computer, it can give you a precise p-value. But when you're using a table, you're not going to get precise answers.
We haven't seen that yet.
Huh?
We haven't seen it like that.
P-value less than 0.001?
We,
I think we have.
oh, last, maybe
We
last
should have.
year, but-
Yes, yes.
So our entire final mountain will all be integers. Does that make sense?
All right.
This part, is there not like an A, B, C, or D?
Yeah, okay, so your practice is like this. The final exam is multiple choice. Okay? So I think I had something similar on last week's quiz, or even on the practice quiz, where it kind of says like, you know, your answer choices are p-value is between 0.02 and 0.05, and p-value is between 0.01 and 0.02, or something like that. You'll have choices like that, and you would pick the correct one. Okay? If alpha is 0.05, what is your conclusion? So in this case, our p-value is less than alpha, so that means we reject the null hypothesis. Exactly. And if this conclusion to reject the null hypothesis is wrong, what kind of mistake is that? Type 1 error, right? So in number 15, our choice was to reject the null hypothesis, right? So if our choice to reject the null hypothesis is wrong, we're hoping it's not wrong, but if it is wrong, then we have made a type 1 error. Good? Okay, so keeping on. Let me take a look at this. Okay, 14%. The researchers believe that 14% of the population is left-handed. A local school decides to see if their students have a different proportion of left-handed people. The school has a total of 1,500 students, and they randomly select 90 students for the study, and they find that 15 of them are left-handed. Is this evidence that the proportion of left-handed students is different from the population proportion? Okay. Are we dealing with means or proportions? Okay, proportions, right? It's very clear. It says proportions listed in the problem many times. Do we have one sample or do we have two samples? One sample, exactly. Okay, and as we're looking at this, we see things like confidence intervals, so we know we're dealing with a confidence interval. Okay, so this shapes how we're going to do our problem. Number 17 asks, what is our sample proportion? That's p hat. Okay, so that is going to be how many people are left-handed out of our sample? 15 out of 90. Okay, so my p hat is going to be 0.1667 if I round off to 4 decimal places. Okay. All right, let's go ahead and just take a moment to list off our data. Okay, so our number of successes are, our x is 15, our n is 90, our p hat is 0.1667, okay, or 1666666, okay? So if we want to make a 90% confidence interval, what critical value z star would we use? Where do we get this number? Okay, for confidence intervals for proportions, we just have those 4 numbers that you need to know, right? So for 90% confidence, the z star, the number you just need to know is 1.645. Okay, there's no table, nothing like that. It's just 4 numbers that you need to know. Again, this is all listed in our study guide, and it says for a confidence interval for 90%, 1.645 right here. Yes?
When you listed out your values, that x15, that's not p, that's x?
Yeah, because p we generally reserve for proportions, okay? So x is the count of how many are left-handed. So p hat is 15 over 90, and the p that we're testing in our population is, it would actually be 14%.
Calling that x.
Yeah, I'm calling the count that 15 of them are left-handed as x. Okay. So number 19, when making a confidence interval, what's our standard error? Okay, our standard error, so for number 19, because it's a confidence interval, our standard error is going to be p hat times 1 minus p hat over n. This is very different, or not very different, but it is different from when we do a hypothesis test. In a hypothesis test, we use p0. Okay? For a confidence interval, don't forget that you're using p hats. Okay? And again, it's all kind of sorted out here. I don't know if you can see it, but in the for the standard error for one sample proportions, it says p hat 1 minus p hat over n. Okay, and that's when you're doing a confidence interval for proportions. So I'm going to put in 0.1667 times 1 minus 0.1667 divided by n, which is 90. Taking the square root of that, and get 0.0393. Number 20 says, when making a confidence interval, what will be the center of the interval? That's going to just be p hat. 0.1667, okay? And again, if you weren't sure, you can check the study guide. For one sample proportion, p hat is the center. Okay, so go ahead and we're going to make a 90% confidence interval. So that's p hat plus or minus z star times our standard error. So I have 0.1667 plus or minus 1.645 times our standard error of 0.0393. And when I do this, on my low end I get 0.1021, and on the high end I get 0.2313. Okay, and at number 22 asks, based on our interval, is this evidence that the proportion at the school is different from the nation? The proportion of the nation. What is the national proportion? The nation's proportion is 14%. Okay, and our confidence interval for the school proportion goes from 0.1021 to 0.2313. Okay, so is 14% inside? Could 14% also be the school proportion? And the answer is yes. 14%, yeah, is within the confidence interval, so the school proportion could also be 14%. Okay, the school proportion could be 14%. Basically, 14% is inside the interval. It doesn't mean that the school proportion is 14%, but it could be, okay? So the answer to 22, is this evidence that the proportion is different from the nation? The answer is, so it is not evidence, okay? That the school proportion is different from the nation. Don't say that it is evidence that it's the same as the nation. That's not a correct statement. You can only say it's evidence. It's not evidence that it's different. So saying that it's not evidence that it's different is not the same thing as saying that it's evidence that it is the same. And I know these double negatives kind of get us and whatnot, but these are important distinctions. Is that okay? Questions? All right, so we will keep going. All right. It says you buy a bag of Starburst candies and a bag of Jolly Ranchers. The Starburst has 80 pieces and 12 of them are cherry flavored. Jolly Ranchers, there's 70 pieces and 14 are cherry flavored. Assuming that these are truly random assortments, does this provide evidence that Starburst and Jolly Ranchers have a different proportion of cherry flavored candies? So, a very important question here. Are we dealing with proportions or means? Proportions, right? And do we have one sample or two? Two samples, okay? And as we look, it says we're going to do a hypothesis test. Okay, let's list off the data given in our problem, okay? So sample 1, it says are our Starburst candies. And it says 80 pieces total, so N1 is 80. And how many are cherry? 12. So X1 is 12. Sample 2 will be Jolly Rancher. There are 70 pieces, and 14 are cherry. Okay, so I'm going to go ahead and just calculate p hat 1 and p hat 2. So p hat 1 would be 12 over 80, and if I calculate that, I get 15%, and p hat 2 will be 14 over 70, and that will be 20%. Okay? So again, taking just this little moment to kind of sort out all of our numbers will make our lives much better or much easier as we go through the problem. So 23, let's write the appropriate hypotheses, okay? So when we're dealing with two sample proportions, the hypotheses will always be P1 is equal to P2. Or it could be written as P1 minus P2 equal to 0. These are exactly the same. These are the hypotheses that we'll use for this, okay? The alternative hypothesis depends on whether it's a one-sided or two-sided test. Okay, what does it say? It says, do we have a different proportion? So that means we're using a not equal, right? Or conversely, we can write P1 minus P2 not equal to 0. Number 24 asks, what is the value of P hat? So P hat is X1 plus X2 over N1 plus N2. So I have 12 plus 14 divided by 80 plus 70. I have 26 over 150 equal equal to 0.1733. All right. 25 asks, what is our test statistic? Okay. Our test statistic is going to be P hat 1 minus P hat 2 divided by our standard error. And our standard error is equal to the square root of, this crazy thing, P hat times 1 minus P hat times 1 over N1 plus 1 over N2. So just putting in all of this madness, I have 0.15 minus 0.20. And the standard error, I'm just going to go ahead and just go for it. 0.1733 times 1 minus 0.1733 times 1 over 80 plus 1 over 70.
Is that P hat 1?
It's just the overall P hat. So number 24, we calculated the overall P hat. Okay. And when I get this, I get negative 0.81. Do I need to punch this in the calculator, or are you guys okay with doing this stuff in your calculator? You guys did okay on the quiz, so I'm thinking you're okay, but anyway, you do this, you should get this number. Is that okay? Number 25. Okay, so for number 26, how do we get our our p-value from our z-score? We're gonna look this up in the z-table, right? And how do we get our p-value? Well, because it's a not equal sign, what do? We take the area away from 0, the tail area, and we multiply by 2, right? So because the alternative has not equal, our p-value is the tail area times 2, okay? So our tail area is, so we look up z equal to negative 0.81, and in this case, because z is negative, the tail area is the area away from, is just the stuff given in the table. It's the area to the left. I don't have to do 1 minus anything, right? So from the table says when you look up z equal to negative 81, it says the area you get is 0.2090. That's the area to the left. Table says 0.2090. I don't have to subtract from 1 because it's negative. This is the area to the left. This is my tail area. So my p-value is 2 times the tail area. So my p-value is equal to 2 times 0.2090. My p-value is 0.4180. Yes?
You multiplied 2 to the z-score.
I looked up the z-score. My z-score is negative 0.81. I got that from problem 25, right?
Right.
So my z-score is negative 0.81. I look up negative 0.81 in my z-table, okay?
Right.
And when I look at that up, the table says 0.2090. Okay, I don't have to worry about subtracting from 1 or anything like that because we're looking for the area away from 0, and because it's negative, that is the area to the left.
So you didn't multiply 2 to...
I didn't multiply 0.81 by 2. I'm taking the tail area of 0.2090 and multiplying that by 2 and getting 0.4180.
That was my question.
Yes.
You were multiplying by 2.
Yeah. So I'm multiplying my tail area by 2 to get 0.4180. So that is 26. 26 is 0.4180. 25 is negative 0.81. P hat is 0.1733. Okay, and so the conclusion, number 27, is what? My p-value is greater than my significance level of 0.05. So we do not reject the null hypothesis. That means no evidence of different proportions of cherry flavored candies. Are we good? Okay. So let's okay, so let's look at 28 through 33. And again, we're looking at caffeinated drinks, and we're looking at reaction time. So do we so we're dealing, so I'm just going to go ahead and say we're dealing with means. We have two samples. Okay, we have those who drank caffeine and those who didn't. And it says we're doing a hypothesis test. Okay, so let's go through and list off the data that we see. So sample 1 is those who drank caffeine. And sample 2 is those without caffeine, right? No caffeine. We look at this, 30 people, so N1 is 30, no caffeine. N2 is 25. Those who drank caffeine, don't get distracted. It says 300 milligrams of caffeine, but that's not what we're measuring. We're measuring the reaction time, 580 milliseconds. So X bar 1 is 580, and the standard deviation is 110. X bar 2 over here is 640 milliseconds with a standard deviation of 130. Okay. Number 28, we want to know what are the hypotheses. Okay. And so the question says, is this evidence that drinking caffeine improves reaction time? Okay. So I'm gonna write these right here. So 28. So the null hypothesis is easy. It's going to be mu1 is equal to mu2. Okay. All right. So when we talk about improving reaction time, does that mean it takes you longer or less to respond to an event? It takes less time to respond to an event, right? That means you have better reaction time. Improved reaction time means you take less time to respond to an event. So should the caffeinated group, group 1, mu1, should that be greater than or less than mu2? Less than mu2, okay? So, you know, read the question carefully and ask yourself, should mu1, group 1 be larger or smaller? And in this case, improves reaction time means, you know, you take less time to respond. So that's mu1 is less than mu2. Okay. Observed difference in means is going to be X bar 1 minus X bar 2. So that's 580 minus 640. I should see negative 60 milliseconds. That's 29. Number 30 says, what's the resulting test statistic? Okay, so my test statistic is going to be X bar 1 minus X bar 2 divided by my standard error, where the standard error is equal to the square root of S1 squared over N1 plus S2 squared over N2. So my standard error is the square root of 110 squared over 30 plus 130 squared over 25. And if I do the math there, I get 32.85. So my test statistic is 580 minus 640 divided by 32.85. I get a test statistic of negative 1.826. Okay. 31, what's the p-value? Okay, so the degrees of freedom is n minus 1. So I'm going to use the smaller n. I'm going to have 24 degrees of freedom. And I'm going to look up this number 1.826, my test statistic, right? So we go to our reference tables. 24 degrees of freedom, 1.826. I see that it's in between the columns for 1.711 and 2.064. So my tail area, which is my p-value, is going to be between 0.025 and 0.050. Okay, so that's my p-value. So 32, if alpha is 5%, what conclusion do we make? We reject the null hypothesis. We have evidence that caffeine improves reaction time. Yes, question.
So if this was a not equal, we would multiply 2 to our
Yes,
p-value
yes.
numbers, correct?
If it was, does it change reaction time? Then we would multiply these by 2.
And if it was greater, like just say if the sign
Yeah.
was greater, do we subtract it? Is there anything that we
So if the sign was greater, then technically the number you get here should be positive. Okay, but we got a negative number, which matches the fact that we got a less than. Okay, so when you have a less than sign over here, the number you get over here for your test statistic should be less than 0. Okay, which it is. We got negative 1.826. If this was greater than, this number should be greater than 0. That's kind of the ruling here when it comes to t-test. That's that.
Wait, I'm sorry, can you say that last part?
I'm not going to stress about it too much, but basically, if your alternative has a less than sign, your
Right.
test statistic should be less than 0, and it is. Okay. If the alternative has a greater than sign, your test statistic should be greater than 0. Okay. And if there's a mismatch, then basically the answer is don't reject the null hypothesis. You don't even have to worry about looking up p-values and things like that. Okay, but I'm not going to worry about that. I've written the test questions to kind of match this, what's called a directionality check. So I just want you to see that if it's a not equal sign, you're going to take your p-value and double it.
Gotcha.
Okay.
And but we'll just, if you said if it was positive, you could just look at your p-value and then.
Yeah, you can look at your test statistic, and if the test statistic sign doesn't match what the hypotheses say it should be, then you can just stop there and say, don't reject the null hypothesis. You can skip over looking up the p-value step. Okay, but I didn't really stress that too much in the teaching of the course. Okay. All right, number 33. If this conclusion is wrong, if our conclusion to reject the null hypothesis is wrong, what kind of error is that?
Type 1?
That's a type 1 error. Okay. Type 1 is if you mistakenly reject the null. Type 2 is if you don't reject the null, and that's a mistake. Yes.
I'm really sorry to have to ask this again. Why are we rejecting the null hypothesis? What's the rule on that again?
So it says use alpha equal to 0.05.
Oh.
Okay.
So if it's above or equal?
Yeah. So our p-value is between 0.025 and 0.05, which
it's
makes
less,
it
you
less
reject
than
it.
0.05, and that's why we're rejecting the null. Is that okay?
Yeah.
Okay. All right, let's so we're going to look at number 34 through 39. Okay, and so when you read this problem, you see we're looking at proportions. we have 2 samples, and we're going to do a hypothesis test. Okay, let's list off our data. We have the police department, this is sample 1, and we have sample 2, which is the fire department. Okay, the number of people at the police department that were sampled, 200, so N1 is 200, and the number of minority employees at the police department was 80. At the fire department, N2, 200, and number of minority employees there, 50. So P1 hat is 80 over 200, 40%. P2 hat, 50 over 200, 25%. The hypotheses, with 2 sample proportions, the null hypothesis is always P1 equal to P2, or I'm going to write it in the alternative form, P1 minus P2 not equal to 0. The alternative, we just want to know, do they have different proportions? So I'm going to write P1 minus P2 not equal to 0. What is the value of P hat? P hat is going to be x1 plus x2 over n1 plus n2. So here I've got 80 plus 50 over 200 plus 200, 130 over 400. That gives me 0.325 as my overall P hat. Number 36. So our z that we have is going to be P hat 1 minus P hat 2 over the standard error. The standard error is the crazy formula of P hat, the overall P hat, times 1 minus P hat, times 1 over N1 plus 1 over N2. So this gives me 0.325 times 1 minus 0.325 times 1 over 200 plus 1 over 200. And when you do all of that math, you get 0.04684. So doing all of this, I get 0.40 minus 0.25 divided by 0.04684. I get 0.15 divided by 0.04684. I get a z-score of 3.20. This is my test statistic, 3.20. And your number might be off by a tiny bit because of rounding, but if you're in... Yeah, so if it's so big that it's not even on the chart, you just have to ask, well, how much is in the tail area? It's going to be smaller than the smallest number listed in the chart, right? So, so if you look up, well, so actually 3.2 does show up on the chart, I believe. 3.20 does show up on the chart. But, whoops. So when we look up 3.20, I get 0.993. But, you know, if I get a number bigger than 3.49, all I know is that the area is going to be even more than 0.9998, okay? So I can just say that, well, whatever it is, it has to be less than you know, at least 0.9998, okay? But in this case, we got 3.2 and we get 0.39s and a 3, okay? So my tail area will be 1 minus 0.9993. So my tail is 0.0007. Because I have a not equal sign, I double my tail and I get my p-value equal to 0.0007 times 2, or 0.0014. It's still a very small number. Okay. So number 38, what is the conclusion you make? reject the null. Okay. Number 39, in the context of this problem, what's a type 1 error? Type 1 is rejecting the null when the null is actually true. So I don't know where I should write this. This means in reality, police and fire department have the same proportion of minorities, but we think they have different proportions. Okay, so in this type 1 error means the null is true, meaning police and fire department have the same proportion of minorities, but we make the conclusion that they don't. And I don't have space to write it up on the board, so I hope it's okay that I just said it out loud. Repeat it. So it means in reality, the police and fire department have the same proportion of minorities, which is basically saying the null hypothesis is true. But we conclude that they are different. We conclude to reject the null. I hope that's okay. We're almost done, you guys.
You're recording this, right?
I am. Well, assuming my computer works. Sometimes it doesn't, but, huh? Yeah, you know. There are worse things in life, but yeah. Sometimes it doesn't work the way I want it to. Okay. Is that okay? 38? 39? Okay. All right, so number 40. Let's take a look here. Okay, potatoes are sold at the grocery store. I don't know what I was thinking when I wrote all of these problems, but okay. So they're sold at the grocery store in 5-pound bags. You decide to weigh a random selection of 10 different bags because you want to make sure that you're getting your 5 pounds of potatoes. Okay. And you find that the average weight of these bags is 5.2 pounds with a standard deviation of 0.3. Is this evidence that the bags at the grocery store have a mean weight different from 5 pounds? Okay, so we're dealing with means. We've got one sample, and we're going to make a confidence interval, okay, because it says center of the interval, right? All right, so let's look at our data. How many bags did we look at? We looked at 10. What was the average weight of these bags? 5.2, and the standard deviation was 0.3. Number 40, how many degrees of freedom do we have? N minus 1, 9 degrees of freedom. The center of the interval, x bar, goes into the center, 5.2. Again, all of these things, you know, I know I'm just kind of flying through these steps, but you can always look these up in your study guide and just say, oh, what am I, you know, what if the question is, what is the center? You know, if the question says, what's the p-value, what do I do? It's all kind of listed out on that guide that I created for you guys. Okay, the standard error, 42, is s over the square root of n. So it's 0.3 divided by the square root of 10. So I have 0.0949. Number 43, what's the resulting 95% confidence interval? So we're going to put everything together. We have x bar plus or minus t star times s over the square root of n. So I get 5.2 plus or minus, and I'm going to look up 9 degrees of freedom, 95% confident. My t star is 2.262. Times My standard.
Where did you get your T?
My T-star, I looked it up in the table. I mean, I kind of skipped that step, but I have 9 degrees of freedom, 95% confidence. So my T-star is 2.262. That comes from the table. %, 9 degrees of freedom. Okay, so I have 5.2 plus or minus 2.262 times my standard error of 0.0949. So let me see, 5.2, I think that's plus or minus 0.215. And so I get 5.415, or I'm sorry, on the low end I get 4.985 to 5.415. Okay, so what is the conclusion that we make? So number 44, okay, 5 pounds is a plausible value for the mean weight of potatoes, or mean weight of potato bags. Okay, because 5 pounds is inside the interval. So, so no evidence that the mean weight is different from 5 pounds. Okay. Is that good? I bought a bunch of macaroni and cheese boxes, and it says, you know, like net weight this, and I dumped them out on the scale because I was curious if it really was. And they all overfill the mac and cheese boxes. They all weigh a little bit more than the net weight. I guess they don't want people to get angry about. Well, I mean, I only did this with like 5 boxes, but how many? Yeah, I had a kitchen scale, so I just wanted to play with it. Okay.
Close?
What?
Were they close?
I mean, they were all fairly close, but they were all, none of the boxes that I bought during my mac and cheese binging days were under the net reported weight, so I guess that's good. The Kraft company being more generous.
There's actually a grocery store being sued, like being prosecuted for fraud for doing that, like doing, you know, like.
Oh, putting less?
Yes, putting less. It's
Oh, see.
I thought you might have gotten it from reading that in the news.
Oh no, I was just excited for my new kitchen toy and was looking for stuff to measure. But yeah, so well, no lawsuit against Kraft from me. Maybe other people were sorely disappointed to lose a few grams of mac and cheese. But at 99 cents a box, your class action lawsuit settlement will be what, 3 cents? So, okay. A fair die should land the number 4 1/6 of the time, and you roll the die 100 times and count how many times it lands on 4, and it lands on 20 times. Oh dear. Is this different from 1/6? Okay, so here we're dealing with proportions. We got one sample, and we're doing a hypothesis test if we read all of these things. Okay, so number 45, what are the hypotheses? The hypothesis is that the proportion that it lands on the number 4 is 1/6, and I'm using p, not p hat. And the alternative is that, is it different? So I'm going to have p not equal to 1/6. 46, what's the sample proportion? Let's list off the data that we see in the problem. We rolled it 100 times, and it landed number 4 20 times, so my p hat is going to be 20 over 100. P hat is equal to 0.2. That's our sample proportion. 47. When performing a hypothesis test, what's the standard deviation of your sampling distribution? This is just a fancy way of saying what is the standard error. Okay? So the standard error is going to be the square root of p times 1 minus p, or I'm sorry, p0 times 1 minus p0 over n. So notice I'm using p0 here and not p hat. Okay, and that's because we're doing a hypothesis test. I don't have the p0 here, but on the study guide it also says, use the p from the null hypothesis. So I'm using 1/6, and I'm not using 0.2. Okay. So one of the distractor or incorrect answers on the test will be what you get if you plugged in 0.2 rather than 1/6. Okay. So be careful. Don't make silly mistakes. Okay, and so you do this and you get 0.03727. Okay, your test statistic is going to be p hat minus p0 divided by the standard error. So we have 0.2 minus 1/6 over 0.03727, and you get 0.89. So what conclusion do we make? 49, we're going to look up Z in the table. Okay, and when we do that, looking up 0.89, the number I get is 0.8133. Okay. Now it's a two-sided test, so I have to double my tail area. Okay. The table gives me the area to the left, and in this case my tail area is going to be the area away from 0, so my tail area is going to be 1 minus 0.8133, which is equal, wait, I think did I look something up wrong? Okay, no, I'm fine. 0.8133, 1 minus 0.8133, so that gives me 0.0867. Yeah. Oh, I'm sorry. I'm 0.1867. I'm multiplying wrong or subtracting wrong. What's going on here? Go away. Okay. 0.1867, and then so my p-value is equal to 2 times that, 0.1867. So my p-value is equal to 0.3743. And so what conclusion do I make? Or did I? Oh, 0.3734. Yeah, I can't. Making all these dumb mistakes here. Okay. So we say do not reject the null hypothesis. Okay. How are we feeling about that? Good? Okay, so that's that for the math problems. And let's take a look at these other ones. Okay, so let's go through the sampling things. So it says Major League Baseball wishes to conduct a survey of its players. Instead of trying to create a list of all the players from all their teams, MLB decides to randomly select 4 of their 30 baseball teams, and they will survey all of the players on those 4 selected teams. What kind of sampling is this? Cluster sampling. Good job. Okay. They want to survey its employees, number 51. They take a master list of everyone in the company and randomly selects 100 of them for the survey. Yeah, simple random sampling, and the key there is that they're taking the list of everyone. Okay, 52, Toll Bridge wants to survey the drivers. Instead of trying to ask all the drivers, they decide to stop every 10th car. Systematic sampling. Okay, is that good? Okay, and then I just list off a few questions here. There's going to be, maybe about, I don't know, 7 or 8, I don't know, a handful of these on the final exam as well, okay? And of course, they're not going to be exactly the same as this. They're going to be different. But yeah, we'll figure it out here. Okay. So, number 53, a bar chart is used for what kind of data?
Categorical.
Yeah, a bar chart is used for categorical data, okay? So, what do we use for numeric data? Histograms are for numeric. What else is for numeric? Pie charts are for categorical. Box plots, dot plots, okay? So think of these things, right? What displays do we use for categorical? What do we use for numeric, okay? These are big hints. In a normal model, approximately what proportion of the data is within 2 standard deviations of the mean?
95%.
Yeah, about 95%. How much is within 1 standard deviation of the mean?
66.
Yeah, about 68%, okay? About 2/3. How much within 3 standard deviations of the mean?
99.
Yeah, almost everything, over 99%, okay?
What's the name of that?
That's called the empirical rule. Empirical rules. I think early on when it talks about the standard deviation, so it's like chapter 3 in the textbook. The intercept in linear regression is our predicted value when x is equal to what?
0.
When x is 0, okay? What is the slope? That's the prediction line. So the slope is how much we expect our prediction to change, or how much our prediction changes when x changes by what? By 1. When we add 1 to x, how much does our prediction change? That's the slope.
You add 1 to x.
If you add 1 to x, your prediction changes by the slope. Your y hat changes by the amount of the slope. All right? You guys kind of remember this? What's a residual? Also from that chapter, right? Chapter 4 on linear regression. Residual is the difference between the actual and the predicted value. Do you remember that? You guys are breaking my hearts here. Okay. Huh?
We've been doing so well.
Yeah, I know. Okay. Okay, if the probability of A and B happening together is 0, then that means A and B are
Exclusive.
mutually exclusive. Okay, or disjoint, yes. Okay. If A and B are independent, what does that mean? No. If they're independent, it means the outcome of one event is not influenced by the outcome of the other. Right? Can independent events be disjoint or mutually exclusive? Yes or no?
No.
No, they cannot. Okay. For a quantitative is another word for numeric. For a numeric variable, if there is only one peak in the histogram, how do we describe the shape? Unimodal, okay? And if there's 2, it's bimodal, all right? What does it mean to be skewed right? Tail goes to the right, but if you had to describe it in words, if you skewed right, do you have outliers that are larger or smaller or no outliers? What do you got? Yeah, outliers that are bigger, right? Skewed left means your outliers are much smaller. If it's symmetric, it means you've got about the same amount that are bigger as you do that are smaller. Okay? Okay, what kind of measures of centers do we have? We got measure of center that's not influenced by outliers. What's that?
Median.
The median, right? Okay, what's the other measure of center? The mean. And how do we characterize the mean? The balancing point, okay? And the median, how do we describe that? The halfway point. The halfway point.
The answer is the median.
For number 58, the answer is the median, yes. Okay? But probably this banter that I just had with you guys here, and all of the questions that aren't these questions, are probably, you might see questions directly related to that, so. Yes, question. These are not bonus questions. They're like, did you remember anything from prior to the midterm questions is what they are, okay? So you do have to know these things, okay? If you get all 50 questions correct, you'll get 110% on the final exam, okay? Again, that paper that I passed out that says you need this much if you want this grade, that's non-negotiable, okay? You need that much if you want that grade, okay? So you know exactly what you should shoot for, and I wish you guys all the best as you study. We'll see you guys next week. It's been a pleasure being your teacher. So.